Hello there, everybody. Welcome to another MCAT ACE lecture. And in today's lecture, we are going to be discussing IR spectroscopy. And IR stands for infrared. So this is a type of spectroscopy that we use primarily in organic chemistry when we want to look at different functional groups. So let's take a look at the general outline. So what we're going to be looking at here is we'll first discuss infrared energy and the electromagnetic frequency spectrum. We'll look at bond vibrations, which is primarily what the IR energy is responsible for, including stretching and bending modes of bonds. So almost like a slinky or a spring, you can imagine that you have an atom on each end and the bond is the slinky. It can vibrate, and it's going to have different frequencies based on how heavy those two atoms are on each end. We'll take a brief overview of IR spectroscopy in relation to organic compounds, primarily how it's used to identify functional groups. And then you can see here we've got some different ranges with the wave numbers. So wave numbers are a way of reporting energy or frequency. And we'll take a look at all the different ranges. We'll go through plenty of visual examples so you can get a grasp on what we're talking about. Then we'll have a vibrational summary. There's a table that is at the end of this outline, and it will help to summarize all of the different frequencies that we would expect. And then finally, we will move on to the practice session. So let's go ahead and get started with some of this content. So infrared, or as I will be referring to it very often in this course, IR energy, and the scale of it. So infrared energy is going to range from around 700 nanometers, which is right on the cusp of the visual light region. So red would be the first one up, and you can even tell by the name infrared. We're right below that. And then it can go up to 1 millimeter, and that's getting very far down on the other side of the region where we're talking about getting closer to microwaves. And microwaves have the ability to rotate molecules, but they cannot stretch and vibrate them the same way that infrared can. So right below the energy of visible light, the IR is generally not detected by the human eye. So when you take a look at the anatomy of the human eye and the rods and cones that we discuss in the eye, those are able to pick up a very narrow band or frequency of light, and we cannot detect things like microwaves, radio waves, and included in that is most infrared waves we are not able to detect with the human eye. And then we can obviously see the visible spectrum, and then once it goes up into UV and gamma rays and X-rays, we can no longer see that again. So the IR spectrum, when you're going to see these reported, are in inverse centimeters, and this is known as a wave number. So you can convert these in order to sort of get back on track with frequency, wavelength, etc. And all you need to do is take 10 to the 7 and divide by the inverted centimeter value, and divide by the wave number, and you're going to see what results is the nanometers. So you'll get the wavelength back, and then we can obviously relate wavelength to the speed of light. We can discuss frequency, and we can start talking about energy. So for example, let's say that we had a vibrational peak on a spectrum at 1700 inverted centimeters. That would relate to 5,882 nanometers. So these are pretty large wavelengths in comparison to that of visible light. So when we get to the visible light region, we're talking about, you know, triple digits. So starting around 700 nanometers, you have the red, and then you can go down to about 400 when you start getting into the violet before you hit UV. So these are much larger. And keep in mind, you have frequency and wave, the wavelength. Those are inversely proportional to one another when we start talking about energy. So bond vibrations. This is what we've been discussing. This is the main mode by which IR operates. It tends to stretch and vibrate bonds. So infrared energy will exist at a frequency that has the ability to stretch or vibrate these bonds. They can also bend back and forth, but it's not going to break them apart. So when you talk about excitation of electrons into unoccupied orbitals, or even ejecting electrons, so removing electrons from a compound, you're talking about UV and X-ray spectroscopy. You are not looking at IR. IR would be too weak in its energy to be able to perform something like that, but it can vibrate the bonds, which is very useful to us. And so in organic chemistry, IR spectroscopy is going to be commonly used to identify the presence of different functional groups. So for instance, an alcohol, an O and an H, that specific bond setup with an oxygen and a hydrogen in between, those are going to have a very narrow area in which the IR frequency is able to stretch that bond. And that means that it'll show up at a certain place in terms of its wave number. So we'll see examples like that as we're moving through. So let's talk first about stretching and the bending modes. So in terms of stretching, which is the main focus of IR, you have two types of stretching that can occur. You have symmetric stretching. So take a look at this amine here, right? We're looking at the NH stretch. When it's symmetric, imagine that you are pulling the atoms in opposite directions, but they're both going the same way. So you're essentially stretching this out so that they're both being pulled almost like silly putty out in one direction. And they could both also come back, right? Just like a spring in the same direction to meet back at the nitrogen. Now you can also have the antisymmetric or asymmetric stretching. And in a case like that, you've got one of them that's in that return mode and the other one is being stretched out. So you can imagine it's sort of going back and forth, but it's not in sync with the other bond. They're alternating when they're doing that. So those are the two different stretching patterns that can occur. And then we also have bending. So a lot of students can get confused with bending, and the way that I like to give this example is take your fingers, your first two fingers, and hold them out in front of you as if they were making a V shape. So this is the way the slide is set up. This is your bond here, okay? So we have things that are known as in-plane bending and then out-of-plane bending. So think that wherever you're holding your fingers up, you have a plane, right? A flat plane that's going through them. So certain types of bending will occur in that plane, and then certain types of bending will move out of that plane. So in terms of in the plane, you have scissoring. The name is obvious. If you took your fingers and you move them together, right? So one going this way, and then the other one going this way, so they meet in the middle, that would be a scissoring bend. And then you can also have what's called a rocking bend. So this would be where one of the fingers, let's say, is moving to the right and the other finger is also moving to the right. Whereas scissoring, one's going right, one's going left, and then they meet together in the middle. Okay, so rocking, take your two fingers and go to the right with both of them or to the left with both of them. They're still in the plane, but they're rocking back and forth, almost like a swaying motion. Okay, and then we have out of plane bending. So with out of plane bending, take your two fingers and hold them directly in front of you. One of them is called wagging, so move your two fingers and bend them down and then bend them back up, okay? And if you could, you'd move them all the way back past being straight and start bending them back to your wrists. And then they'd come back up straight and then they'd move down. So think of just like a dog's tail, right? It's wagging back and forth like this, okay? So it's more, instead of a side-to-side wagging, although you could, I guess, view it like that, we're looking at an up and down, out of the plane wagging, okay? Because the side-to-side is more like a rocking motion. And then you can have what's called twisting. So this is going to be where you would put your two fingers out in front of you, one goes up, the other goes down, and then vice versa. So you're alternating your fingers back and forth. That is a twisting motion for bonds. So both of these are taking that flat plane that you were originally in with the scissoring and rocking and moving in or out of that plane. So IR spectroscopy in relation to organic chemistry, which we've kind of touched on, this can confirm the presence of functional groups, and that's going to be based on where they show up in the IR spectrum. They will have specific wave numbers, which we will look at, that they have associated with them. So some examples here. An alcohol bond is going to show up somewhere between usually 3200 to 3500 wave numbers. And when you look at the alcohol peak, it's also very broad. That's due to the hydrogen bonding that occurs when you have alcohol groups present. So you get these kind of unique peaks that identify functional groups. Carbonyls are not broad at all. They're very sharp and narrow, but they're very, very strong. So they come down as a very long peak. and they're somewhere between 1680 to 1800 inverted centimeters. And sometimes students will say, well, why is there such a large range? Well, that's because there's a whole lot of different carbonyl groups. We have ketones, we have aldehydes, we have carboxylic acids, we have esters, we have amides. So not all of them have the same exact resonance and the same exact type of setup, and therefore you're going to have a large range in terms of the neighboring atoms and how they affect the carbonyl stretching. All right, and then for instance, a carbon-oxygen single bond instead of double bond, that's further down in the 1100 to 1300 inverted centimeter region, and this would be for things like alcohols and ethers. Now, we noted alcohol up here. This first alcohol is for the OH stretch, and then that O is connected to a C, so the second one where we're mentioning alcohol is for the CO stretch. So just keep those separate, right? We have every single type of bond can have its own stretching frequency, and therefore you can have, multiple peaks when you get these IRs. So let's take a look at the functionality that is sort of hinted at or given away above the 3000 inverted centimeter region. That's the first big stop where we look. So this is normally going to be on the left-hand side of an IR spectrum when you're looking at it. And there's a couple of things that can be located here. So number one, you can have CH stretches that are found usually somewhere between, on the low end, just above the 3000, so like 3020 or thereabout, and it can go all the way up to 3300. Now, this is for alkene, alkyne, and aromatic CH bond stretches. Okay, so you're looking primarily anytime you're above 3000, you're looking at hydrogen stretches with various atoms. Okay? Now, the amine is an NH stretch, and that's going to be found between 3100 and 3500, so we're moving a little further up. And what's important to note here is that primary amines are going to have two peaks. So that's because when you're a primary amine, you're talking about an NH2, right, like a terminal amine. And because there are two NH groups, and you can have the asymmetric stretching, you end up with two peaks for a primary amine. Now, if you have a secondary amine, you only have one NH bond, so you're going to have one peak in a case like that. And then for alcohols, the OH bonds, as we mentioned in the previous slide, are around 3200 to 3500, and those are very broad. And then what's interesting here is the carboxylic acids, due to resonance and the way they behave, their OH bonds are found around where the alcohols start, but they are very, very large in terms of how far down they can stretch. So they go almost down into the 2700, sometimes even the 2500 inverted centimeter region, whereas pure alcohols that aren't carboxylic acid based are going to be found around the 3200 to 3500. They'll stay closer to that region. So let's take a look at some visual examples. So here's a primary amine, and the main thing you want to focus on when we're right here is this doublet that is stretching right up here, and you can see it says 3360 and 3282. This is for the primary amine. Now you have two primary amines here, but this molecule is symmetrical. So similar to NMR, when you have symmetrical groupings, you are going to also have a symmetrical signal that's just going to overlap here. So this is a classic example of an amine stretch that's above the 3000 region. So here's another example. We're taking a look at an alcohol here. So you can see the alcohol group in nerol, and look at this broad OH peak. You see how it doesn't come to as fine a point here. You have a much more rounded peak, but this is at 3327. Again, it's in the expected above 3000 range for that alcohol. And I will note, it is possible to get alcohols that are broader than this, and you can also get ones that start to get a little bit sharper. And that really has to do with how concentrated the alcohol is in the sample that you're presenting to the infrared spectrometer. So if you have one that's very, very dilute, the hydrogen bonding will not be as intense or as prevalent, and therefore it will start to narrow. And then if it's a very concentrated sample, you can end up having a broader peak, and that's just a result of more of the hydrogen bonding occurring. So just an interesting fact there. Now let's discuss the functionality that we find in the 3,000 to 2,000 inverted centimeter range. So this is primarily going to be your triple bonds. Okay, you have the alkyne, which is a CC triple bond, and that's going to be found between 2100 and 2200. The nitrile sometimes overlaps that a little bit. It's very close. The nitrile is going to be between 2200 and 2250. So the nitrile is usually a little bit higher in the wave number, but only by a hair, not by a whole lot. And then the other thing I'll mention here, this tends to be ignored, but you can find examples of it all over the place, which is exactly why it tends to be ignored, is the aliphatic sp3ch bonds. So these are just your standard sp3 hydrocarbon bonds, and those are found at 2850 to 2950. But what's important here is that they are not above 3000. So as soon as you start seeing the peaks above 3000, those constitute one of the other groups that we saw. They do not constitute just regular hydrocarbon groups. Now again, why is this ignored? Because it's in almost every single organic compound, so it's on almost every single IR spectra that you're going to take for an organic compound. Hydrocarbons are just prevalent. They're going to be there. So here's an example with an alkyne. You can see this peak right here, the 2108 peak, is for the carbon-carbon stretch. Okay, that's for the triple bond. Now, of interesting note here, you can also see the stretch for the carbon-hydrogen bond involved with the alkane. So remember that we said when we have an alkyne, a CH stretch above the 3000 mark is right here. Now something else that I wanted to note here, see how this says 3311? All right, if you go back and you look at the slide that was presented, it originally said that it can range up to 3300, right? So 3300. A lot of students get caught up in saying, well, this is 11 wave numbers over the suggested range, so therefore this couldn't possibly be the carbon-hydrogen bond of an alkyne. And you cannot get that strict in your thinking. You need to allow, these are general ranges. It can depend on if you're running this in a solvent, if you're running it in what's known as a KBR pellet. There are different modes by which we measure, and different compounds have other different functional groups present that can affect this. So you shouldn't be super stringent with your values. These are general guidelines. However, it would not be appropriate to say, oh, I'm going to say that this CH stretch for the alkyne is located at 1700. Right? That's not where it belongs. But if it's close to the general region, if it's bordering it by, let's say, 50 to 100 inverted centimeters, in general, you should be okay to go with that. Note right here, the other thing I want to point out, look at this peak, right? It is just a hair below 3000, and that's what we were talking about when we were looking at the aliphatic CHs. You're going to find these peaks here all the time, just above just below 3000. But if it gets above 3000, you're looking at some other type of functionality you need to examine. All right, so let's talk about functionality in the 2000 to 1000 region. So here we're going to be looking at carbonyls. That's the most prevalent one that is known in this region. That's the C double bond O, and that's found between 1650 all the way up to 1800. And this includes a wide range of functional groups. We'll take a closer look at that in the summary table. Again, don't get caught up in the individual ranges. So, oh, this has to be an aldehyde, this has to be a ketone. You want to consider other evidence that you might be presented with when you're looking at that. So with an alkene, you're talking about your carbon-carbon double bond, and that's going to be found between 1600 and 1680. So notice we were doing triple bonds in the 3000 to 2000 region primarily, and now we're dealing with double bonds as we get here. And as we get to the lower end, we have alcohol and ether carbon-oxygen bonds, and they can be found as low as 1100 to 1300 when we're looking at those. So here's an example. Okay, right here, what's of interest to us is that we want to look at the O carbon. So it's an ether here. We're looking at oxygen-carbon stretch. And you can see right here, here's the 1,000 mark. So we're staying right around the probably 1,100 mark for this carbon-oxygen stretch. Now, just to reference back to what we had earlier, there's an amine here, right? And so we can see that there is an amine stretching. Now, the two peaks here, you can see the other one's kind of fractured off, and this is a little bit more rounded, so perhaps this was more concentrated in the hydrogen bonding. But you can still see very clearly above the 3,000 range that you have the NH stretching. And then again, you have your aliphatic stretches. Those will be prevalent in almost every single compound that we take a look at. So here's another example. This is a classic carbonyl peak that you're seeing here. So at the 1658 region, right, that's where this amide stretch is going. Amides tend to be due to resonance on the lower end of the inverted wave number for carbonyl range. So they're around the 1650. And then things like the acid chlorides and the anhydrides get up closer to the 1800 region. Okay, again, you have an NH group. You can see your one single peak associated here with the NH stretch. And once again, the aliphatics that are going to be sort of omnipresent in all of these. All right, now the functionality between 1,000 and 500 inverted centimeters. This is a very difficult region, and in general, students should be very careful when they go into this region. So this is known as the fingerprint region, and it's going to be unique to each structure. That's exactly why it's called fingerprint. So just like a fingerprint is unique to each individual human, you've got a unique set of stretches, bends, all of that sort of stuff when you get down in this region. And it can be very difficult to analyze without a database. So if you had a large database and you could basically take a scan of a compound and compare that IR directly to what's in the database, that would be fantastic, because then you could try to align that and take a look and compare the fingerprint regions. But if you're stuck on the MCAT, you're not going to have time to look at the fingerprint region and be comparing it to other fingerprint regions. So this is in general a region I would encourage most students to stay out of. Now, that being said, I do have to bring up one thing, because there is something that's a fairly well-known pattern there. The dye substitution patterns on a benzene ring show up in this region. So if you have ortho substitution patterns, the benzene ring will show about one peak around 750. If you have a meta substitution pattern, you're going to get two peaks, and they will be around 700 and 775. And then for para, if you have a 1,4 substitution pattern, you'll get one peak around 840. So these can still be difficult to determine in the fingerprint region, and that's due to all of the other peaks that are present there. So it can easily get lost in the noise. So I would not suggest you go in looking for it unless you see other evidence, let's say a carbon-carbon double bond or a carbon-hydrogen above 3,000 for one of the aromatic hydrogens. If you see the evidence of an aromatic compound being present, then you might want to go ahead and venture and try to take a look to see if there's a substitution pattern. But in general, this region is noisy. I don't want to say it's useless, but in the context of trying to analyze on the MCAT, it's going to be very limited in its use. All right, so here is a summary of the vibration wave numbers. So we said alcohols are 32 to 35, the amines 31 to 35, and you can go down and you can see the list here, okay? So what I really want to focus on is the carbonyl portionality here, because that we can differentiate some of these. Now again, don't get so caught up in the exact dividing lines, but use it as a general guide. So amides and carboxylic acids, which are going to be some of the strongest in terms of resonance, are on the lower end. So amides tend to be 1650 to 1690, and then the carboxylic acids go slightly above that. They can go upwards towards like just over 1700. Then you get the ketones and the aldehydes. So that's 1715 to 1725 for a ketone, and aldehydes tend to be just above that. Then you get to esters. Esters are a little bit higher. They're around the 1735 to 1745. And then, as I mentioned, the anhydrides and the acid chlorides are going to be on the upper end of this range here. So we're getting much closer to the 1800s. And the anhydride by structure has 2 carbonyl peaks. So you're going to see one at the 1800 region, and then you'll see another one that's still higher than the esters, but it's not as high as 1800. It's usually like a 1760, 1770, somewhere around there. Okay? And the rest of these we've already discussed, but you can always pause the video if you need to here, if you wanted to mark down any of these regions. And with that, I am going to conclude the lecture portion here, and we will head over into solving and practice. Okay, so I have pulled up the questions here for IR spectroscopy. Let's go ahead and take a look, and as usual, we'll go through these. We encourage you to pause the video and try to attempt them yourself as best you can before unpausing it and going for the walkthrough. So, the first sample question here. A reaction of 2,3-dimethylbutane 2,3-diol with aqueous acid affords compound A, whose infrared spectrum is below. And you can see the infrared spectrum here. Right? Which of the following structures best fits the IR spectral data for compound A? And these are the options you have here. Now, I do want to point out that this is supposed to be based on the IR, but if you had a working knowledge of organic chemistry reactions, you could predict the product without having to really deal with the IR in general. But for the purpose of this, I want you guys to look at the IR and attempt to correlate it to a specific structure. That's really the goal of this exercise here. All right, so here are the choices, and you want to match that up here. So obviously, you want to take a look at the functionalities that are present, and we have some different ones. We have an alcohol, we have a carbonyl, we have a ring system with an epoxide, and we have a carbon-carbon double bond. So, based on the peaks or lack thereof that we find up in the different wave number regions for the IR, you should be able to answer that question. So that's question 1. And then question 2 states the following. Ethyl benzoate is expected to display prominent absorption in which regions of the infrared spectrum? So you've got 3 different ranges here, and these are all going to correlate to some type of functionality that could potentially be there. Now, these ranges should make sense because we went over all the different ranges and what could potentially show up there. So when you're looking at this, you want to keep that in mind and think what could show up in, the 3200 to 3500 wave number region. What could show up in the 1700 to 1750? And based on that, the answers A, B, C, and D are what you're going to pick from. So you want to go through 1, 2, and 3, see if they're plausible for ethyl benzoate, and then based on which ones are, you're going to pick the best selection that you can find down below. So those are the questions. Here's the second one. Take a look at it for a second. Pause it if you need to write it down. And I will show the first one more time. Okay, so the first one, we've got the information up there, but the important part here is the IR. So take a good look at that. You can pause the video here if you need to analyze it. And then these are the potential compounds. So go ahead and pause the video, work on these problems, and when you're ready, unpause it and we will continue forward. Alright, so hopefully everybody had a chance to work on this. Now we're going to take a look at the answers. So for the IR spectrum of compound A, you could approach this in one of 2 ways. You could either start dissecting the IR spectrum and attempt to find any important peaks there, or you could go down to the answers and start eliminating them one by the lack or confirmation of peaks that you find up there. So I'm going to do the latter of these choices. I want to start going through and looking for certain functionalities. So for A, I know that A, what I would focus on is the alcohol. Okay, now why the alcohol? Because the rest of this is all just sp3 aliphatic CH stretching. Every single one of these compounds is going to have that. We all have CH3s in each of the answers. So that's not going to be of much use to us. And if you remember in the lecture I stated, that's almost an omnipresent peak. And that peak is going to be right here. That's the one that's just shy of 3,000. You would expect to see that in almost every organic structure that you come across. So we're going to ignore that peak when making these decisions here, right? Now, I continue to look, and the alcohol, I do not see an alcohol peak. I do see a very tiny peak up here, okay, that I don't know that that really correlates to anything in the structure for A, but it's certainly not an alcohol, right? An alcohol would have a nice big broad rounded peak that's coming down in that region, and that's not what I'm seeing right now. So I can certainly eliminate choice A from the pool of choices. All right, then I get to B. B has the aliphatics, but the most important part of B is that I've got the carbonyl here. So the question is, do I have something that looks like a plausible carbonyl? In this case, absolutely, okay, because here's about 1600 and right here's about 1700. So I certainly have a carbonyl somewhere in that region, especially when I have such a strong peak there, right? Then this is certainly possible. So we're going to keep this in the running, and we're going to look at the other ones here just to make sure. Now what's interesting is because I probably have a carbonyl peak there, I can eliminate anything else that doesn't have a carbonyl. So remember that we're all about saving time when we're doing this type of, problem solving, especially under the idea of MCAT. So that means there's no carbonyl that I find in C, and there's no carbonyl that I find in D. So let's not spend time going in and searching for carbon-carbon double bonds and everything else. If we already can see there's a prominent carbonyl peak there, we're just going to toss these out and go with B, because that saves us more time. And that's, in terms of what you would want to actually execute on the MCAT test, that type of decision making is ideal. So B is going to be the correct answer for the structure above. And if you do know the organic chemistry here, when you're doing this, you're taking the alcohols, you're getting rid of them, and then you're turning it into the corresponding ketone that's here. Okay? So, ethyl benzoate is expected to display a prominent absorption in which region of its infrared spectrum? And you've got a couple of them here. All right. So let's think. In the 3200 to 3500 region, we're going to have a couple of potential things. We could have some CH bonds. We could have, and these CHs are for sp2 carbons, so things like the aromatics, the alkenes, the alkynes, right? We could have an alcohol stretch, and we could have some sort of an amine stretch, right? So that's number one. And then if we look at number two, 1700 to 1750, this is going to most definitely be the region where I would find a carbonyl stretch, okay? And then number three, 1580 to 1610. So in this region, I most likely have something along the lines of a carbon-carbon double bond, right? And this could be for the alkene or the aromatic when I'm looking at that. So those are the different potentials that we have. Now we want to look at and analyze which of these is most likely to show up when we're actually analyzing ethyl benzoate. So one of the things that would help is if we know the structure of ethyl benzoate. So maybe you do or maybe you don't. Ethyl benzoate's not horribly complex. I would hope that most students taking the MCAT would be able to conclude what it is. The bens should indicate that you have a benzene ring. Well, that's a good start. And then the ethyl benzoate. So when we talk about ethyl and ate is referring to that we have an ester. That's the way that we would name an ester compound. And the ethyl is referring to what's on the other side of the ester. So we're looking at a structure that looks like this, right? Now let's correlate this to the options that we have above. So let's start with number one and dissect it a little more carefully, okay? So for 3200 to 3500, we mentioned that we have CH with sp2, but I want to mention that you need to be careful here because the CH stretching that's associated with this is most likely going to be for a triple bonded carbon to a hydrogen. the aromatic stretching that you would find of a hydrogen is going to be closer to the 3,000 to 3,100 region. All right, so it's on the lower end of the 3,000 region. It is above that 3,000 mark, which is an important distinction to make before we get to the aliphatics. But I would argue that when we're talking about this, okay, this is more for the triple bond than it is for the alkenes, okay, the aromatics and the alkenes. So that is not present in the structure. So I would go ahead and I'd get rid of this, even though it's over 3,000 usually. Now, what does fall much more in the 32 to 3,500 region are alcohols and amines. They're further up on the wave number list there. But I do not see any alcohols or amines associated with this. So most likely, I would want to get rid of one, okay? Now, if I do that, I could automatically say then that means A is out and that means D is out, right? So I'm left with B and C, and both of them have 2. So let's look at 2, and if 2 can be eliminated, then the answer is definitely C. So 2 is without a doubt a carbonyl group, and we do have a carbonyl group present because we have an ester. So these are both possible right now. So now it's going to come down to, is 3 present or not? So 3 in this region is going to be very distinct for a carbon-carbon double bond, and that can be for alkenes or for aromatics. So because we have an aromatic ring and we do have that C-C double bond, this would be present, and so therefore B would not be correct because it's only accounting for the carbonyl, and C is the correct answer. So just to give a little reminder or further clarity for 1 in case people were confused, okay? When we had 1, we initially put that CH could be up in that region, but it's primarily for the carbon triple bond to the hydrogen. And when we start talking about that, okay, that is a little bit high. So what we would have needed to see in terms of the range is something that said more along the lines of maybe, let's say 3,020, and I'm just making this up here, to 3,150 or something along the lines of that. If we were on the lower end of that, okay, then we could potentially say that yes, 1 would also apply, and then D would have been the correct answer. But in this case, these are simply too high for the CH stretch that we're looking for. So I just wanted to clarify that one more time in case people were confused. What I was originally listing up here is basically anything that showed up above 3,000, because that's how we broke down those ranges when we initially looked at them. All right, so that concludes the problem solving for infrared spectroscopy. I did want to briefly just show you, here is the ethyl benzoate IR, and you can see all of the different stretches that we have here. And note, here at the 3078, we do see, right, this little peak right up here, we do have the aromatic stretch. It's not that it's not there, it's just that if we go to the 3200 to 3500 region, which I sort of just boxed off there, we don't see anything. That's a little bit too high, okay? We certainly have the aliphatic stretch. Here's our prominent ketone peak that we would be expecting, right? And here are the double peaks that we get for the aromatic. Remember, you usually see 2 of them when you've got an aromatic stretch in that region. So that concludes all of the practice, and it also concludes the lecture for the IR spectroscopy. So we hope that you found everything useful, and we look forward to seeing you in additional lessons. Take care, everybody.